Good morning. First of all, many thanks to the organizers for the invitation to talk. It has been a great pleasure to be in this workshop, and I enjoyed the talks with everyone so far. I will tell you about high-frequency gravitational waves in Axion Experiments, and this is work based on these two papers, which were done in collaboration with Valery Domke and Nicholas Roth. Okay, so here is the outline of my talk. Before discussing anything, I will motivate why I'm interested in high-frequency gravitational waves. Then I will draw a parallel between gravitational waves and Axion electrodynamics. I will try to convince you that these are really closely related phenomena. Then I will discuss applications of these ideas in laboratory experiments, cavities, and other detectors. And then, before concluding, I will discuss the application of these ideas on cosmological scenarios. Okay, so motivation. Gravitational waves have been discovered in the last 10 years, and they open up a new window for the universe. And this is the paper of the LIGO-Virgo collaboration, where they first describe these gravitational waves by the merging, this paralleling and the merging of black holes. Here I want to emphasize two things. The first one is the frequency range of these black holes is of the order of 100 Hertz. This is related to the length scales associated to this process. And actually, it's very hard, or actually it's not known, how to produce gravitational waves of frequencies higher than 10 kilohertz in astrophysical objects. That means that finding signatures or signals of gravitational waves with frequencies above 10 kilohertz is discovery of physics beyond the standard model, physics, new physics. Okay, so that's the motivation. And in fact, there are many sources of gravitational waves in that regime, and they are all associated with early universe phenomena. So inflation, cosmic strings. Okay, there are many examples, and actually now there is a growing community that is seriously considering the search of high-frequency gravitational waves. Okay, in the talk, I will try to convince you that even though we are still far from probing early universe phenomena, there are many ideas, and yeah, we are making progress towards that goal. Okay, here I'm showing you a paper that is actually a living review, where all these things are discussed. And okay. So one of the main proposals of detecting gravitational waves of high frequency is related to Axion experiments. And this is due to this parallel between gravitational wave electrodynamics and Axion electrodynamics. So what is Axion electrodynamics? I think okay, in this audience I really don't have to explain too much. But I mean, the bottom line here is, okay, if you write down the Maxwell equations in the presence of an axion field, you get this. So you get, the homogeneous equations, and then the inhomogeneous equations can be cast in this way. So you can define a charge current or a charge current density in this way, and a current in this way. And even though these objects are not associated to electric particles like electrons or protons, effectively this behaves as a current. For instance, this current is conserved, and it has all the properties that you expect for a current. That means that one can study the magnetic fields that are produced or that are induced by these currents. That's the field of Axion electrodynamics. And you all know here that this leads to very rich phenomenology in different experiments, different astrophysical and cosmological scenarios. Here is a few examples, and it's of course an incomplete list. Essentially, you have helioscopes that aim to detect the conversion of axions into photons in the presence of a magnetic field. You also have haloscopes. So in this case, the axion doesn't come from the sun, but from the galactic halo. Or you have purely lab experiments, such as those that are aiming to detect light shining through the wall. Okay, so this will be important afterwards in my talk, so I will explain in my words as a theorist how a cavity works. So the essential idea here is, okay, you have axions from the galactic halo, right? So like in a cavity, in an experiment on Earth, you have an incoming axion, or axions that are there, because that's dark matter, right? And then, according to this current, or according to these currents, the presence of the axion in this cavity will give rise to a current, right? So inside the cavity, you generate a current if there is an axion and there is an external magnetic field, okay? This current will, in turn, induce an electromagnetic field, right? And if the electromagnetic field coincides with one of the modes of the cavity, then the experiment resonates, and then you detect a signal. So these are all examples of cavity experiments. And okay, here you can see these are actually Maxwell's equations written for the cavity. And right, so here you see the effect of the effective current, which is exciting the modes of the cavity. So the same thing I said in words is in this equation, okay? This will be very important for what I would say afterwards, essentially because really what enters in these equations is just the effective current. Okay, then you have, if we go to lower masses for axions, you have this technology, so technology based on loop element detectors. We have heard about this a lot during the workshop, but the idea is very similar to the case of cavities. So in this case, I'm illustrating what happens in the case of abracadabra or shaft. So in those experiments, you have a toroidal magnetic field. This is illustrated here in orange, okay? So if you have an axion if you have the axion field associated to dark matter, which is supposed to be in the galactic halo, according to the equations that I wrote at the beginning, you get an effective current, right? So these are one of the Maxwell's equations, the Ampere's law, and in that, in the right-hand side, I have an effective current associated to the fact that the axion induces a current due to the presence of the external magnetic field of the toroid, okay? Now, if you just use, for instance, Biot-Savart law, this current will induce a magnetic field at the center, right? So if you put a pickup loop, this current will generate a signal on that pickup loop due to the magnetic flux that is induced at the center, okay? So this is, I know this is a bit perhaps simplistic, but in my mind as a theorist, this is how these things work. Okay, so we already know also that there is going to be an impressive progress in the following years in these sort of experiments, and actually this is what it is expected for the dark matter radio program, which is based on that technology. Okay, so why is this important? Okay, the reason why this is important for what I'm saying is because, as I said, all these things are based on the fact that you generate an effective current. Well, if you write down Maxwell equations in the presence of a gravitational wave, you generate an effective current. So it's the same concept, same idea. This is just what you get when you write down Maxwell's equations in the presence of gravitational waves. This is the effective current. Is of course a bit more complicated because it involves the gravitational wave. In this case, it's not an axion, so this has a different structure, but conceptually speaking, is the same, right? I want to emphasize a few things here that are important, especially for people who are not experts. This is not quantum gravity. This is just classical electromagnetism. There is nothing here of physics beyond the standard model, okay? This is just, as I said, write down Maxwell's equations in the presence of a gravitational wave, okay? So that's point number one. Point number two, even though it is useful to think of this as a graviton conversion into photons, that's not necessarily what is needed to describe this phenomena, because the only thing I need is this effective current, and you don't need to think of quantum of a quantum picture. Okay, so just to summarize, what I'm trying to say here is this is classical, pure classical physics. Okay, nothing fancy. Good. So how do we detect this in laboratory? So how does this work in practice? Well, in practice, what happens is that, well, first of all, as I said, there are many possible ways for axions. Once you have an effective current, the same thing happens for gravitational waves. There are many possibilities of applying this idea, but the simplest is the case when a gravitational wave is converted into an electromagnetic wave in the presence of a magnetic field. And in fact, these two processes, the conversion of axions into gravitational waves, the conversion of axions into electromagnetic waves or photons in the presence of a magnetic field is strictly analogous. So actually this analogy has been studied for a long time, and in this paper by people in the audience, this analogy is really very clearly explained. In fact, what you have is, to describe this, you just have a two-level system, and then you describe the oscillation of one state into the other. And yeah, the same thing you do for axions, you do it for the gravitational waves. Nothing really different, except for the fact that the effective current has a different structure. But formulas and many of those things are easily adapted from axion physics to gravitational physics. This effect, so there are two things that I want to mention here that are, I think, curiosities. So this effect has been known for a long time. This is called the Gerstenstein effect. So the conversion of gravitational waves, well, the conversion of gravitational waves into electromagnetic waves is the inverse Gerstenstein effect. This was studied by Gerstenstein in the 60s. And it actually, I think it's remarkable that the same person, a few years after this paper, proposed to use laser interferometers, so optical interferometers, to detect gravitational waves. So he was trying to think or to conceive experiments for the detection of gravitational waves, and he was the one who, one of the persons who predicted or that proposed the idea of interferometers for the detection of gravitational waves, which is actually how they were detected a few years back by LIGO and Virgo. Okay, so this guy had all these ideas already in mind. Good. Okay, so how does it work in the experiments that we know? There is this very nice paper of a few years ago that actually calculated this effect for different experiments, for different Axion experiments. And so these experiments, like ALPS or OSCAR, they are light shining through the wall experiments. So I mean, I don't have to explain to you how that works. But I mean, the idea is very simple. You have a source of photons. Then, in the presence of the magnetic field, this can generate an axion, let's say a WISP. Then the WISP goes through the wall, and then in the presence of an additional magnetic field in a different place, you can create a photon, right? So light shines through the wall, right? So you can use this experiment. You just forget about what happens on the left and just consider what happens on the right. So if you have an gravitational wave, the gravitational wave will be converted into a photon in the presence of the magnetic field, right? So you can then use the observations by these experiments to cast limits on the amplitude of gravitational waves. This is what you get, okay? This is very interesting. Something that, okay, this is some hypothetical source. It's not so important to understand what this is. This is just like a hypothetical source from the early universe. What is important here is that, and this is super important, actually in this field it's the holy grail, is this nucleosynthesis limit, okay? So for those of you who don't know about this, this is a limit on gravitational waves that exists due to nucleosynthesis. So we know that, we know how to explain the abundance of light elements after the Big Bang, and that requires that the universe doesn't expand so fast. So if you have extra radiation, like that of gravitational waves, this will destroy this picture, and therefore we can get a limit, assuming that we just have ordinary nucleosynthesis, okay? So that means that any signal of gravitational waves that was produced before Big Bang nucleosynthesis must be below this limit, right? So that means these experiments are still far, I mean, look at the scale, are still far from this BBN limit, okay? So that means, okay, we are still far from probing inflation. Inflation would be here, down this line. So, but of course, the goal is to reach this line. I mean, and that's what we all want to do in this field. And yeah, that's the, as I said, this is the holy grail. We want to reach this line. Right. So here is also the limit of cast and also projections for Yaxo. Good. Keep in mind the frequencies here. We are talking about very high frequencies. Good. Far from testing early universe signals. I emphasize this. And then now, after discussing this light shining through the walls experiments, now let me talk about cavities. Good. So in cavities, as I said, the idea here is you have an effective current. It could be either that of axions, or it could be the effective current induced by the gravitational waves. That effective current can excite the modes of the cavity, and it can make it resonate, right? This is how gravitational waves could, in principle, be detected in this cavity. This is from a paper of some colleagues of mine, friends of mine actually, many of them, who described this phenomena recently. So less than a few months ago. This is the results. So this is what you obtain for a limit in the case of all these experiments. Okay, I know most of you are actually involved in this experiment, so I think it's very interesting. They more or less agree on this 10 to the minus 22. I will explain to you later why this is the case and why that is not a coincidence. Right. So that's microwave cavities. And then in 1 minute or so, I will, a word of caution here. There was this paper a few years ago who was claiming that ADMX had the potential to probe gravitational waves only if they rotate the magnetic, the external magnetic field. So they proposed this idea of rotating the magnetic field to describe, to detect the gravitational waves. It turns out that's not correct, and the reason is they did the calculation mixing two different gauges. So this is a bit technical, and this paper pointed out. So they say, okay, you have to be very careful. Actually, this is well known in the gravitational wave community. You know, gravitational waves are like electromagnetic waves, so you can also choose a gauge, and you have to be very careful because, so the standard assumption actually is that, okay, it's easier to describe gravitational waves in something that is called the TT gauge, but it turns out that that's wrong, and you can't, well, it's not wrong. I mean, you can do it, but then you have to make sure that you also describe the cavity in the TT gauge. So in the TT gauge, the cavity moves. And this is, so the walls of the cavity move due to the gravitational wave. So calculating the eigenmodes, it's more involved than usual. So what they propose is like, okay, as it is done for all other gravitational wave experiments, instead of using the TT gauge, you should use something called the detector gauge, or the detector frame gauge, Once you do that, the cavity, the walls of in that gauge, the walls of the cavity don't move, and then you have a signal. So, and they just recalculated what ADMX can do, and in fact they found that they don't need to rotate the magnetic field. In fact, the data that they already collected can be used, and they use it to set a limit on gravitational waves. So the message here is, so for those of you interested in gravitational waves, be careful. We all know that you have to be careful when you choose a gauge. So that also applies for gravitational waves. And for the experimentalist, good news, ADMX doesn't have to change anything. The way it is good enough because they can detect the gravitational waves. Good. So I thought that was an important thing to say. Now let me talk about haloscopes based on these toroidal magnetic configurations. So as in the case of cavities, there is a direct analogy with axions. So in this case, a gravitational wave enters this region where there is a magnetic field. The magnetic field sources an electromagnetic current in this toroidal field, in this toroid, and then you can use the Biot-Savart law to calculate the magnetic field here at the center. Okay, this is the magnetic field that is produced to leading order in frequency, to frequency square. So you see, it's very interesting. It's different. I mean, even though the conceptually speaking is the same as in axions, the fact that this is an object with helicity 2, or a spin 2 object, if you want, makes this slightly more involved. So the magnetic field, you see, so on the left, the magnetic field is negative, on the right is positive, and I'm talking about the piece of order omega square. So that means that if you put a circular pickup loop, the circular pickup loop will not detect a signal of order omega square. In fact, it will detect only, so as it is, it will only detect the leading, so the next order, so the order omega cube. So that means the flux associated to gravitational waves will be suppressed by the frequency cube. That's not so good because, of course, we are aiming at very low frequencies, and so that means suppression. That's one thing. The other thing is, okay, you get a signal, but only for one polarization. Gravitational waves, for those of you who don't know, carry two polarizations. They are typically called H cross and H plus. So these are just polarizations of the wave. And this experiment, as it is here, will only be able to measure H cross polarizations. Okay. So is there something we can do? Well, before discussing that, let me tell you that the fact that that you have a suppression with the frequency means that you have an enhancement with the volume, right? So the suppression with the frequency comes with an extra volume factor. So that means that if you compare with axions, the sensitivity scaling with the volume is faster for gravitational waves for this scenario than for axions. So progress will be faster for gravitational waves if you just keep it like this. Okay, actually, just to compare, this is the signal that you would get for axions. Okay, so it's very similar, as you can see. Okay, it's very similar, but you don't have frequency suppression for the axions, and you don't have angles. That's also interesting. So a gravitational wave is something. I mean, we assume here for this exercise a plane wave. So of course that means that it carries a direction. So here this means the sign of the angle square. So the signal will have directionality. Of course, this is already suggesting that if, I mean, let's dream, let's suppose that Abracadabra finds axions and gravitational waves. So it's both. So that means that one can do things like rotate the experiment or conceive things like, okay, studying the directionality of the signal to tell axions from gravitational waves apart. Good. These are the limits, and actually this is very interesting because we managed to derive with this scenario, limits at these frequencies, actually these are the best limits we know at this frequency. I mean, it's very weak, 10 to the minus 4, but they are limits. So Abracadabra and Shaft already put limits on this plane. So these are really limits on gravitational waves. They are very weak, but they are nevertheless there. And then this would be the progress of the dark matter radio program in this plane. Okay, so I think it's relatively interesting. And then you see there is this strong dependence on the frequency. That has to do with this thing that I just described. Good. So to overcome that this problem, we propose an idea in our paper. Okay, so as I said, this is an experiment that was designed for axions, but that doesn't mean that you cannot just modify it or change it or conceive another experiment so an experiment that is designed for the specific purpose of gravitational waves. And one obvious modification that is very simple that occurs to this occurs to theorists. Of course, I know experimentalists will do much better. But if you, instead of putting a circular pickup loop, if you choose this a figure 8 loop, then you improve, you get rid of this problem. So you get rid of the frequency dependence issue. And interestingly, you get both polarizations now. So you can get a signal for the H plus and the H cross. Okay? So a very simple modification proposed by theorists allows to measure both polarizations, whereas if you don't do that, you can only get one of them, and you get rid of the cubic suppression on the frequency. Now is frequency square, and actually there are theoretical arguments that tell you that you can't do better than omega square. It has to do with the fact that this is a gravitational wave. Okay, right. So now. I think I have like, what, 10 minutes? 10 minutes, okay, good. So what can we detect with this? I said like 10 minutes ago that signals from the early universe are still very far from this. So in our paper, we included what would be the signal associated with a black hole merger. So this has to be a primordial black hole, so it's not an astrophysical black hole like the ones that LIGO detected. So it has to be something like this. And but it's interesting because you see, we are not that far. So for these experiments that were not designed for gravitational waves, we are not that far from reaching this. So I know that the dark matter radio program is very ambitious and that this will not be reached in the next year. But I do think that, so I'm sure actually, that's my, what I think of this. I'm sure that there are ideas or there are things and proposals that can be made to reach further down, okay? And that's the challenge here. So trying to go here and eventually to the BBN line. This is actually, this includes a lot of effects that were not known before we wrote the paper, and actually simultaneously some other group of people actually also found this line. So this is really like very new things that happened in the last few months, okay? So I invite you to have a look at the paper if you want to know about the details of this. And right. So now let me tell you about these sort of ideas in a cosmological context. So it turns out that there is a certain evidence, or I don't know if you can call it a strong evidence or not, but so there are these objects that are called TV blazars, and it turns out that it's very hard to accommodate observations by different telescopes if you don't have a cosmic magnetic field. So this is a bit of complicated astrophysics, but I think at the end of the day it's not so difficult to understand. All this suggests that there is a minimum value for the cosmic magnetic field. So this was the situation when I actually started working on this, because we were thinking, okay, there are these experiments on Earth. So I'm talking about like 2 years ago. We were saying, okay, there are these experiments on Earth that are measuring or attempting to measure gravitational waves, but how does that compare to what you can get using these cosmic magnetic fields that people are also talking about in the last 10 years? Observations by Fermi, Hess, this is from 2010, I believe. So, right, so we said, okay, let's calculate what would be the bound that these sort of magnetic fields give. Okay, so, so let me first go, So forget about the right-hand side and let's just focus here. So on the left-hand side, so this describes, this plane is how you describe cosmic magnetic fields. On the one axis, you have the value of the field. In the other axis, you have the coherence length. And this lower limit that I said when I discussed the Blazer thing is this. So, right, and then there is an upper bound from observations of the CMB. If these cosmic magnetic fields are too strong, then they destroy or change the CMB anisotropies. That's not good, so that gives up an upper bound. And then these are theoretical bounds from magnetohydrodynamics, okay? And then on this plane, so you can use these things to calculate the Gerkenstein effect and calculate what are the probabilities. These are contours of more or less, I mean, probabilities rescale in a dimensional way. So this is like a probability for a fixed frequency. Okay. So let me go back to so we have this process in the early universe. You have this process in the early universe. You have these cosmic magnetic fields. Then the gravitational wave can be converted into a photon. And if you look at the CMB, for instance, that extra photon can stand out of the CMB. We know, observationally speaking, nothing stands out of the CMB, which is a perfectly, it's a perfectly described spectrum with a Black-Body law. So one can place a limit. Okay, this is what we did back in 2000. So last year, 2021. And right, so and then there are also these observations by edges that can also, that probe also this Rayleigh-Jeans tail. So we have observations by arcade and by edges, and we put a bound using the fact that these things don't suggest something above the Rayleigh-Jeans tail. And that gives you this limit, okay? Well, as I said, this is not impressive, so don't, I mean, we are still far from an effective, as I said. Our exercise was, okay, is this giving me a stronger stronger bounds than experiments on Earth? The answer is, it depends. So if you are, if the magnetic field is here, so if it's very close to what this Blazer observation suggests, then more or less, if you are here, if we are very close to the CMB bound, then by far arcade and edges are better than experiments on Earth, okay? What I wanted to tell you here is that there is a strong parallel between Axion electrodynamics and gravitational wave electrodynamics. One example is Axion photon conversion. The other example, so the equivalent of that, the analog of that, is the Gerkenstein effect, which is gravitational wave conversion into photons. In both cases, you generate an effective current. And actually, in our paper, we wrote it in this way. I mean, it's very interesting that you can do this. So P and M are just effective vectors for the people who are familiar with with electrodynamics in continuous media. This looks very similar to what these vectors P and M that are used to describe condensed matter systems look. So, and you see, so this is just math. I mean, it's a convenient way of writing it. So you see, for axions, you can write down, or you can cast the current like that. For gravitational waves, you cast it like that. So you see, there is a very clear connection, right? So in one case, you have this, So the Axion is CP odd and gives you this. For gravitational waves, you have the this Hij, which is the gravitational wave, but now it is determined by the electric field, not the magnetic field. And then, finally, I wanted to tell you that in our paper, we also show that once you reach the QCD axion line, that for haloscopes, so the QCD line for haloscopes, that's regardless of the frequency, that's equivalent to detecting a strain amplitude of the order of 10 to the minus 22. So the conclusion, since I put everything together, so arcade, edges, the dark matter radio program, the different cavities, what you will expect for these black holes, primordial black holes, in spiraling. And then the conclusions are, well, Axion experiments may discover not only dark matter, but also exotic sources of gravitational waves. And, right, so all of these proposals are more or less coinciding on this effect, this strain of 10 to the minus 22 at the megahertz regime. And we still don't know whether this will be useful for detecting signals from the early universe, but of course that's the goal. And yeah, that's what I hope, and the people that wrote the paper with me also think the same. So thanks a lot, and now I can take questions.
Okay, thank you for the nice talk, Rika. So we have a question.
Thank you for a great talk. What would be the spectral signatures of these events? Because these experiments are all kind of optimized to look for this narrow axion signal of a narrow bandwidth.
Yeah.
I assume the spectral characteristics are different for gravitational waves. Could you comment on that?
Yes. So, okay, this line that we draw here was for the specific experiment that we had in mind when we wrote the paper, which was abracadabra, so a broadband detector. So we also mentioned in the paper that we have to be very careful when comparing all these things because, as you properly mentioned, I mean, for instance, cavities, they are not broadband, so they really measure an individual frequency. So in that case, this signature will not be exactly the same. It will be corrected. Yeah, I don't know if this answers your question. But the point is, it's going to be similar to an axion signal, not difference.
Yeah, I would like to comment that we have a nicely controllable gravitational wave source, lab size, which is the LHC for 11 kilohertz. And there was a workshop on this about 1 year ago. And there's no need to go in the far field, so you can put up a near-field gravitational wave detector, sort of super Cavendish experiment, half a meter from the beam pipe. And there were all kinds of ideas to use this for calibration, including phase lock techniques to get a few microhertz bandwidths.
Yeah, thanks a lot for the comment. And yes, a lot of activity in this field, many ideas. People are proposing things all the time. So this is really like a growing field.
Hi. I have a question. I think slide 18. Okay, I think slide 18 you had limits on using the light shading through wall experiments, and they were around, like, the frequency range was around 15 hertz, and they're much, I guess, narrower than the Axion limits. Can you comment on the frequency ranges and why it's different for?
I actually don't know. You're talking about this, right?
Yeah, I'm talking about that.
I don't know what determines this. I didn't do these plots myself. Andreas knows. Well.
I mean, ALPS is using an optical laser, and therefore the detector, which was exploited in ALPS, was sensitive at the electron volt range, frequency range, and electron volt are 10 to the 14 hertz. So this is just because of the detector. And YAXO is kilo electron volt because they look for solar axions. The detector was an X-ray detector, and X-rays are at 10 to the 18 hertz. So it's just so if you put another detector at a YAXO, a microwave detector, you could get a sensitivity at much lower frequencies.
I know there's probably a quick question quick questions because we need to run out of time.
Brilliant talk, thank you.
Thanks.
More physics with the same apparatus, but the point is, can you tell us why the frequency scaling is better than the Axion?
Better. Well, actually,
You said it's faster than Axions.
well, I don't know.
There,
So
yes, that's it.
It's not better, it's worse, no? Because we want to go to low frequencies, so it suppresses the signal. Why is that? Why do you have this? As I said, this is just a consequence of the pickup loop. So if you change the pickup loop and you put it in this way, you get omega squared. Now, it will always be proportional to omega squared because it's a wave. You can prove this using GR. We did it in our paper. Also, the paper by the people who were doing cavities, they also prove that it has to go with omega squared in the best case scenario. This is a property of gravitational waves. Yeah.
Okay, well, let's wrap it up here for this, and then we have our, so it's just a clap for this.